So this is just a review over sections 2.1 and 2.2. We're going to go over average rate of change, instantaneous rate of change, what they are, what they look like, how to find them, and also 3 conditions for a limit to not exist. So looking at this first part here, we have average rate of change versus instantaneous rate of change. So first, whenever you see the words rate of change, you want to think slope. So for average rate of change, if we're interested on the rate of change between 2 and 4, for example, what that would look like on a graph is you have your value of 2 here, your value of 4 here. Average rate of change is just the line between them and the slope of that line between those 2 points. So how we find the value of the slope of this line, it's just the same slope formula that we've been using. So the slope formula is just difference in the y's over difference in the x's. And that'll give you the average rate of change between these 2 points. For instantaneous rate of change though, what if we're interested in what is the rate of change exactly at the point x equals 2? What's the slope of that line there? So this line here, it's called the secant line. It touches the graph at 2 points, not just the first time, but also a secant time. The line here, though, is a tangent line. It touches the graph at exactly 1 point. So if we're interested in the slope of this line here, we're not able to use our slope formula because we only know 1 point on the line. We don't have a second point to use for a slope formula. So since we can't calculate the slope of this line directly, instead what we're going to do is we're going to get a bunch of points really close to our point of interest and calculate the slope of those points with our point of interest and see what those slopes are equal to in order to estimate what this slope is that we're actually interested in. Okay, so our step 1 is make a table. And like we just said, we're going to plug in points closer and closer to the value we're actually interested in. So here's my x, here's my f of x. If I'm interested in the slope at x equals 2, I might plug in 1.9, 1.99, and then going from the other side, 2.01, 2.001, etc. So step 1 is make a table of values approaching my point of interest. Step 2 is actually find the slope between those values and what I'm interested in. So I'd find the slope between 1.9 into 1.99 into, and so on until I go through all my points. So brief recap, average rate of change represented by a secant line on the graph. To calculate average rate of change, you just use a slope formula between those 2 points. Instantaneous rate of change is represented by a tangent line on the graph, and you estimate that by making a table of x values approaching your point of interest, and then finding slope between all those values. Okay, moving on to the 3 conditions for a limit to not exist. Our first one is if the right-hand limit is not equal to the left-hand limit. Using some shorthand over here. And what that looks like on a graph is, let's say left hand is going here, and the right hand, it jumped up, it looks like this now. As you can see from the left-hand side, it's approaching a different value than what it is at the right-hand side. Now, a brief note about this, I could put an open circle here, could put 2 open circles there, or I could fill one of them in, or I could have filled in this one. The only way this can't be true is if I fill in both of these. So if we're going to fill in both of these circles, that means that this is no longer a function, because the function has 2 different y values at this same x value, right? So just brief note about that. Make that an open circle. Okay. Condition 2 for a limit to not exist is if the function is oscillating. That means that it's going up and down super quickly at this one point. You can't tell what value the function is approaching. An example of this is the function sine of 1 over x. So sine of x usually is a periodic function. It goes up and down at a regular pace, but the function sine of 1 over x, as it gets closer and closer to 0, it starts oscillating super fast up and down from both sides. This is a really crude drawing, but it goes something along those lines. So the limit as x approaches 0 of this function sine 1 over x doesn't exist because it's oscillating so frequently and so highly at that point. Okay, third condition for a limit to not exist is if it's approaching infinity. And so what this might look like on a graph is if there's an asymptote here, it could be approaching either negative infinity or it could be approaching positive infinity. Either way, the graph is going to start getting closer and closer to that asymptote, but it will never actually reach a value. So because of that, the limit does not exist in that case. So this is a brief recap of 2.1, 2.2, and how to solve these types of problems. Hopefully this was helpful.